All right, let's get started. So I'm going to be working through the 2025 FRQs from your green packet. Uh, so we'll start on page 23, and if we have time, we can look at some 2024 FRQs, but my main focus is on the 2025. Uh, if you look under 59510, I also have link to the video for the 2024 FRQs. So I've already recorded that. So that's my main priority is just making sure I can record the 2025 FRQs, and then you can reference the last year's video if you're working through the 2024 ones. Uh, I do want to make sure that you guys look through these topic predictions. It doesn't mean that these are going to be the topics that you're going to for sure see on the AP exam, but these are the ones that have come up the most often in recent years. So rate in, rate out, integral problems. If you see these problems involving, rate of something being added and rate something of being removed, then a lot of times it's involving this initial plus amount added minus amount removed. And then a lot of times extreme value theorem gets worked into that problem as well. So kind of knowing, some of these subtopics that these AP writers tend to gravitate towards can be helpful. If we're looking for these things, and we know that these are topics that they have to some in some form or another have to um, uh, involve on this AP exam. So they're kind of restricted. They have to ask these types of problems somewhere along the FRQs, and typically they're going to show up within these specific problems. So if you see extreme value, so if it's asking for greatest or least, you're always starting building your AFT function, and then you're finding the derivative. And if it's in the calculator section, you're just going to graph that A prime and look for the x-intercept. And then once you find your critical points, then you test them against your endpoints, against your function, along with your endpoints and critical points. Riemann sums, typically mean value theorem falls into that category. A lot of times you're asked about approximation using slope, and but they give you a table of values. They usually are asking about approximate the area using left rectangle, right rectangle, trapezoids. Watch out for first theorem. A lot of times they're trying to get you into that first theorem. So knowing this formula and knowing how to apply it sometimes can be really helpful. If it's a particle motion problem, then know that final equals initial plus displacement. I feel like you're almost guaranteed to see a table of values, and you're almost guaranteed to see a derivative graph as well. So if you're given a derivative graph, you know that you can create your slope sine line, use that slope sine line to find your relative max, relative min, increase, decrease, points of inflection. Sometimes extreme value theorem works its way into a derivative graph as well. Second theorem sometimes works its way into it. If it's solving differential equations, a lot of times it shows up in the non-calculator section. So you may have to either build a slope field or sketch a slope field of some sort. Sometimes watch out for related rates. Related rates is going to, if it doesn't show up in different equations, a lot of times it shows up randomly in the part C or part D of an FRQ. So the way you spot related rates is they start mentioning time a lot. With respect to time, they give you um, uh, uh, something like meters per second, inches per second. All these mentions of time is indicating, okay, you've got to most likely you're going to build a derivative from your equation and then attach a d over dt for each of your equations. Um, Yeah, if you're given and then L'Hopital's rule, those are easy to spot, limit problems. Tangent line equation, linear approximation, sometimes they work itself into different equations. Sometimes they also see them in Riemann sums as well. Um, Function table of values, if you're given a table of values, a function table of values, sometimes they may ask you to find the derivative, and depending on how things are set up, it could be a chain rule, product rule, quotient rule, implicit. First theorem works itself into those problems sometimes. Use substitution. Sometimes you have to find the integral using use substitution. If it's an area volume problem, typically you have area between curves, you have volume, either disk, washer, or cross section, and then sometimes use substitution problem, especially if it's non-calculator. If it's non-calculator, typically you can expect at least one use substitution problem that they want you to work through by hand. Okay, so let's start with your AB FRQ. This is page 23. If you're in BC and you're here, I think in your yellow packet, it's going to start at a different page, but uh, we're going to you're going to have those FRQs as well. So we're just going to work through the AB FRQs, uh, and then after 10 o'clock, I'll do another session for the BC students going over the BC only problems. Okay, so this is calculator. An invasive species of plants appears in the fruit grove at time t equals 0 and begins to spread. The function c defined by c of t equals 7.6 arctan of 0.2 t models the number of acres in the fruit grove affected by the species t weeks after the species appear. It can be shown that c prime is equal to. So it's nice. They're giving you the derivative of c of t. So they're giving you a head start. So you don't have to build that c prime on your own. Okay, it's also nice that they're telling you to be in radian mode. I just sent out a reminder to all the classes that make sure you check your calculator. We should always be in radian mode. Okay, so make sure you're always in radian mode. But ultimately, it really only impacts if you're dealing with trig, but I think it's just safer to just always be in radian mode, and that way you never have to change it. Again, over the course of the test, just always leave it in radian mode. Part A, find the average number of acres affected by the invasive species from time t equals 0 to t equals 4. Show the setup of your calculation. So we're trying to find the average number of acres affected. We know C of t models the number of acres. So we simply have to go through average value theorem um, as we build out our as we find the integral. So average value theorem basically which is 1 over b minus a, integral from a to b of f of x dx. So for us, our a and b values will be extending from 0 to 4. That's our time interval. And then our f of x is going to be our c of t function. Okay, calculator. Arctangent, you just do inverse tangent to same, it's the same thing, just different notation. Use x in your calculator. Math 9, but I'll do alpha trace first. 1 over b minus a, 1 over 4 minus 0. right? 2.778 acres. Part B, find the time when the instantaneous rate of change of C equals the average rate of change of C. So look at the wording here. Instantaneous rate of change, that's basically derivative, equals the average rate of change, that's basically slope. So they're trying to get you into mean value theorem without actually stating mean value theorem, but they're describing it very explicitly though. So you're basically involving C prime, and then here you're involving the slope between the two endpoints. So uh, problem is trying to get us into mean value theorem. So let's remind ourselves what mean value theorem is. It's where you take your average rate of change and you match it to the instantaneous rate of change. Right, that's mean value theorem. So my average rate of change would be, in this case, C of 4 minus C of 0. My function is C. And then my derivative is C prime of T. So C of 4 is just plugging 4 into the C of T function to get my order pair at 4. And then C of 0 just means plug 0 into the C of T function to get the Y value at that point. So just going to go back and find my order pairs here. I already have Y1 holding my C of T function. So I can just do alpha trace Y1 of 4. So there's my Y value for my order pair there, 5.1 or 4 comma 5.12. And then at 0 is 0. Okay, so Y of 4, or in this case C of 4, is going to be minus C of 0, which is 0, over 4 minus 0. Right? I'm just taking my order pair and building out my average rate of change. Equals C prime. The nice thing is they're already telling us what that C prime is, so we don't even have to find the derivative. We can just bring it down from what they have for us. So the problem says, find the time when the instantaneous rate of change equals the average rate of change. And this is a calculator, so we're going to make the calculator find that variable for us. So I'm just going to put this in the calculator here. Well, at least I would like this to be a little bit cleaner here. So 5.128 divided by 4, going to get 1.282. So this is potentially a messier equation to solve. I guess we could solve for t if we algebraically clean this up. Another way, because we have our calculator in front of us, why don't we just graph this? We could just graph this. And then if we set equal to 0, then we can just graph and look for the x-intercept. You can do this in your graphing calculator. You can do this in Desmos. So I'm just going to choose to graph it here. Remember to use x for your variable. I'm going to adjust my window here. We're going from 0 to 4. And let me just go from -10. Oh, my scale, I don't want to change that. My Y min, Y max, I'll go from -10 to 10. So I see an x-intercept there, but it's kind of hard to see. So I'm gonna make my y values shrink a little bit. So let me go from, let's say, -2 to 2. Let's see if that will get my graph to have an easier time showing me. Okay, so I see an x-intercept there. I'm looking for an x-intercept. So do second trace 0, pick a point to the left, and scroll over to a point to the right. 2.154. Okay, so I have my t value there. This is in terms of t is in terms of weeks here. So find the time t. So we're 2.154 weeks in is when our average rate of change will match the instantaneous rate of change. Here, they're asking us to solve for t. They're not asking us that can we guarantee this value. So there's no need to specify all the conditions that are involved with mean value theorem. Here, they're saying that this is true. This is going to happen, and we just have to connect this with mean value theorem and actually just go through the formula and adapting mean value theorem for our problem. Okay, part C. Assume that the invasive species continues to spread according to the given model. Write the limit expression that describes the end behavior of the rate of change in the number of acres. So end behavior just means limit as we approach infinity. So we want to find the end behavior of the rate. So the rate is talking about C prime, is not talking about C of t. So we're just going to take the limit as we approach infinity of our C prime. So we have a different set of rules when we approach infinity. If we're approaching a real number, we like to plug in and see what happens. But with infinity, remember, we compare degrees, right? We compare degrees between numerator and denominator. Numerator has a lower degree than the denominator. So if the denominator is growing at a faster rate than the numerator, then this fraction is getting smaller and smaller. And if it gets smaller and smaller, and if we continue that trend towards infinity, my limit is going to be approaching 0. Part D, at time t equals 4 weeks after the invasive species appear in the fruit grove, measures are taken to counter the spread of the species. The function a, defined by a of t, so this mess of a of t here, models the number of acres affected by the species over the time interval from 4 to 36. At what time does a attain its maximum value? So there's a key word here trying to get us into a specific way of working this problem. And they're mentioning finding a maximum value. That should hint to us that we're going to be working with or applying extreme value theorem. Apply EVT. And again, with EVT, we have two things that we want to do, right? We want to test endpoints, and we also want to test critical points. And critical points we do by setting the derivative equal to 0, right? So Once we know we're dealing with EVT, our first next step is trying to find critical points to test because we already have endpoints. We could just go ahead and start putting the 4 and 36 into the function, but we need something more, right? We need to figure out some more critical points. So we have to find the derivative, set equal to 0, find that critical point, and then consider them in addition to the endpoints. So let's build our derivative. So derivative, we have a of t. Let's get to a prime of t. I'm just writing out a of t again, just so we can have a frame of reference, but let's build a prime now, a prime. C just becomes C prime, so that's in function notation. We just leave it in function notation. Which we can reference later, right? C prime is just going to be this, so we can bring this down later. But C prime minus, we also want to find the derivative of this, so let me just show what I want to do. I want to find the derivative of this integral. And we know when we see this type of notation, or if we're trying to find the derivative involving an integral, we know they're just opposite operations. So they're just going to kind of undo each other, take each other out, remove each other. And so we're just left with that 0.1 natural log of x, but the t gets inserted. So 0.1 natural log of t. Okay, so a prime, let me bring in that c prime that we're going to be working with. 38 over 25 plus t squared. And to find critical point, we're going to set equal to 0. So just like before, we're going to use our calculator. We're going to graph this. And we're just going to look for the x-intercept. And that will help us find a critical point that we can use in addition to the endpoints to use as our candidates. Right, so 30, put that in. Let me see if I can adjust my window here. For part D, they say that our interval is from 4 to 36. So I'm going to just make my x min, x max from 4 to 36. Previously, I had my bounds being -2 to 2. So let me see if that will still hold. So I'm going to hit graph, see if I can find some x-intercepts. So there's only one. Right? So just second trace, 0. Pick a point to the left of my x-intercept, hit enter. Then pick a point to the right of my x-intercept, hit enter. 11.44. So I have a critical point at 11.44. I'm going to round that 1/7 to 2. So we have one critical point. and that's our one critical point that we found. The endpoints are using 4 and 36. So we're going to take these endpoints and critical points. We're going to put them all back in to my AFT equation. Right, because AFT is going to tell me the number of acres that are affected. So is number of acres going to be affected the most at 4 weeks, 36 weeks, or 11.442? So we're just going to plug into our AFT equation. So my CFT, I'm just going to have reference that again. So CFT, I'll put it under Y2. Oops, Y2. So I'll spell out what I want to do here. So C of 4 minus the integral from 4 to 4. So the nice thing initially is that the integral from 4 to 4, there's just 0 out. So this won't give me anything. So just C of 4, give me 5.128. So now let's do A of 11. Eight 8.807. Math 9 from 4 to 1.49. And then 8.807 minus 1.49, 7.317. All right, last candidate is my endpoint, A of 36. So all I'm doing is I'm just putting it into this formula here. So C of 36. 1.743. So we're looking for the absolute maximum. So we're looking at 5.1 versus 7.3 versus 1.7. And the maximum that we see is going to be that 7.317. But the problem is not asking for the amount of acres impacted. It says find the time where the max occurs. So we can say at t equals this is what they're asking for. Okay. Number two. Also calculator. The shaded region R is bounded by the graph of the function f and g. F is the one that is below, and g is the one that is higher up. Find the area of R. Show the setup for your calculations. So area is just top graph minus bottom graph. Integral. The top is the g of x function. The bottom is the f of x function. We just do math 9, enter all that in your calculator. Five point 1.366. Part B. Region R is the base of a solid. For this solid at each x cross sections, so we know there's a volume involving cross sections here. And we're told how to draw our base length. It says perpendicular to the x-axis. So that is indicating that we're dealing with vertical bases, right? Vertical base. And we want the shape of a rectangle with height height x, and the base in the region R. So we know we're always going to be starting off with the base length. So base is, in this case, vertical base, vertical basis. So top minus bottom. The top is sitting on the G. The bottom is sitting on the F. Just distribute the negative through here. Okay, so what area do we want to build? We want to build an area involving rectangles. So area of a rectangle is base times height. And they're telling us the height is x, right, with height x. And then the base, we can just pull that from what we just built. So now we have an area expression. And remember, we don't want to plug anything in. When we're at this area stage, we want to hold on to all the variables that we're working with. If you want to distribute through, you can, but you don't have to, because the next step is the volume. So volume is taking your area and then accumulating it over the course of my entirety of the bounds from 0 to 3. I want to just put the X in front. It doesn't really matter. I'm just showing that I want to multiply, represent my area somehow. Okay, Math 9. I got 7.7049. Part C, write but do not evaluate an integral expression for the volume of the solid generated when the region is rotated. So you see the word rotation, revolving, you know it has to be either disk or washer method, right? So we're rotating about the horizontal line y equals -2. So I'm just going to use the diagram and draw it in for part C here. So here's my horizontal line that I'm rotating around. And if we look, the dotted line is nowhere near the shaded region. Also, if it were touching, it will still be washer method. There is no flat surfaces anywhere here. No matter where you draw the axis, there's going to be a gap. So we know it has to be washer method. So that means we need to draw two radius. One radius that extends from the dotted line to the furthest boundary. It's my big R. And then my small radius will from the dotted line to the closer boundary, the nearer boundary. Okay, so let's build R, big R, uppercase R of X first. Big radius is the top of my big radius minus the bottom of my big radius. So the top is sitting on the G of X. Minus a -2. So careful with your negatives, with your signs there. My small radius is, in this case, the top minus bottom. The top of my small radius is sitting on the f of x. My f of x is the x squared minus 2x. Minus a -2. Which will end up being +2, right? Okay. So now it says write but do not evaluate. So that's nice. Don't have to put in the calculator. Just have to set it up, set up the integral. So bounds from as far left as 0, as far right as 3. And then my big radius. Make sure you square your big radius separately from your small radius. Right, each radius is getting squared, pi out in front. This is as far as we need to go because it says write but do not evaluate. Part D, it can be shown that G prime which is 1 plus pi cosine of pi x. They're giving us g prime. Find the value of x between 0 and 1 at which the line tangent to the graph of f is parallel to the tangent of the graph of g. So basically, tangent of graph of f is basically f prime. Tangent to the graph of g is basically slope involving g prime. So we simply have to figure out when is f prime equal to g prime. So they already gave us g prime. We just have to get f prime on our own. But g prime, they tell us, is 1 plus pi cosine of pi x, which is nice. They could have asked us to find that on our own. We could have done it on our own as well, right? We could have gone through power rule and sines derivative cosine of u times u prime, but they're giving it to us. F prime, we have to build that on our own, but that's easy. That's just power rule. So that's just 2x minus 2. So we're simply setting them equal to each other and solving for x. Now, we don't have to do this. We don't have to solve our x on our own because we have our calculator. So you could graph them separately and look for the intersection, but I just always prefer to bring everything over to one side. And then simply look for the x-intercept. Oh, it's x. Okay, I want to graph this. And because I don't want to have to look at competing graphs here, I'm going to go up and unhighlight those equal signs so that the only equal sign that is highlighted. And I'm looking for the x-intercept here. They say between 0 and 1, so I'm just going to adjust my window to just show from 0 to 1, so I'm having to. So let's see where that takes me. Yeah, x-intercept here. Second trace, 0. Okay, so enter. Pick a point to the right of the x-intercept, hit enter, and I get 0.6758. Okay, so that ends the calculator section. We're moving into the non-calculator. Number 3. A student starts reading a book at time t equals 0 minutes. It continues reading for the next 10 minutes. The rate at which the student reads is modeled by a differential function r. R is measured in words per minute. Approximate r prime of 1. So you see the word approximate. That's going to have to be slope related. We know that r prime is a level down from r of t. We don't have enough information where we can find the derivative at 1, but the next best thing is slope. Slope is the algebra version of calculus. So I'm just picking the t-value that's closest to 1. So I'm going to choose 0 and 2. And oops, sorry, not r prime, r of 2 minus r of 0. So change in words per minute over the change in minutes. Okay, so our units of measure, notice that R of t is already a rate, it's already words per minute. So if I do a slope on top of that rate, then it'll be words per minute or words per minute squared. And they're going to ask you for units of measure, which we already did. But it says show the word that leads to your answer. Um, I want to go one step further because a lot of times the problem will ask you for this. A lot of times they want to ask you, interpret the meaning or what does this mean? So even though for this problem you could stop here and not have to go any further, I do want to extend this problem a little bit because we see this so often. Imagine this problem also said interpret the meaning or interpret your answer. I know again this is not part of the problem, but I think it's good for us to practice this step in case they ask you for it. So understand that anything that is involving the second derivative with these rates of change, word problems, it is not particle motion here, so we can't say acceleration. We want to say something along the lines of our rate is, in this case, positive, so our rate is increasing. So this means that the student's reading rate is increasing by 5 words, or at a rate of 5 words per minute squared. I'll put in parentheses to indicate this is not part of the problem, but a lot of times we want to make sure we know how to do this. So the key words here they're looking for is um, rate is increasing, right? Rate is increasing. That's showing understanding of what's happening with that second derivative or how to talk about that second derivative. Part B, must there be a value? So anytime I see the word must there be a value, I'm thinking, okay, they're trying to ask for a guarantee. And a lot of times it's either going to be, is it IVT or is it MVT? Usually it's going to fall under one of those two camps. So either we're a slope away from the guarantee or we're at a level where we can indicate that guarantee. So if you look, we're at the level that the data is providing us, R of t. And we don't have to worry about slope because if it was asking, can we guarantee where r prime is equal to 155, then we have to think about, okay, how can I create a slope of 155 from my table? But here, we're at the level that they're referring to. So this is a little bit easier because we just have to look for a value above 155 and a value above 155. If we can find that, and we know that the graph is continuous, right? Because it says modeled by differentiable functions. So differentiable means smooth. If it's smooth, that means it's going to assume continuity. And so we do see that, right? So we see a value below 155. We see a value above 155. So we can guarantee that between 8 and 10, my R of t has to pass through 155 somewhere along that. So for part B, sorry, I can say this. I can say R of t is differentiable and therefore continuous. So we do want to establish continuity, but because they're giving us differentiable statement, we have to show that we understand, okay, you're telling us differentiable, but we're also, even though we don't need differentiable as a condition, that's the starting point, and we're just saying that, okay, we know that we need continuity, and we're connecting this word with continuity. Okay? If you're telling me that it's differentiable, then I know that my condition of continuity will be met. So we have a R of t value below 150. That's coming from R of 8. And we have a value above 155, which is coming from R of 10. And 155 is safely between my two values that I see. And so there must then be a value of C on the interval from 8 to 10, such that f of C equals 155. There's more than one way to say this with IBT, but this is the one that we can use where we can use the least amount of notations and words to get our point across. Part C, use the trapezoid sum with 3 subintervals indicated by the table data in the table to approximate the depth integral from 0 to 10 of R of t. Show the work that leads to your answer. So this is pretty straightforward. Trapezoid, we can just set up our intervals here and identify the width by subtracting the t values, and then we can pull the heights from the second row from the R of t. So remember, the formula for trapezoid is 1/2 width times height 1 plus height 2. So we just have to go through and build out 3 trapezoid areas for our 3 subintervals. And remember, this is non-calculator, so leave unsimplified. Don't try to spend all your time adding all these values together when you can just string all these messy parts and leave it alone. Okay? Don't have to get it down to 1252, just stop here. Okay, so 1/2 width, my first width is 2, and then height 1 plus height 2, so 90 plus 100, that will be the area of my first trapezoid. Second trapezoid is width of 6, so 1/2 times 6, height 1 plus height 2, and then third trapezoid, 1/2 times width 2, and then height 1 plus height 2. And just stop here. Part D, teacher also starts reading at time t equals 0 minutes. It continues reading for the next 10 minutes. The rate at which the teacher reads is modeled by W of t. So understand W of t is a rate. W of t is measured in words per minute. Based on the model, how many words has the teacher read by the end of the 10 minutes? So we know that we are trying to get this W of t into something that is a different function because we have words per minute. That's not what we want. We want something in terms of words. So to get from a rate up to without the minute here, we have to take the antiderivative. So to get to antiderivative, we'll take the integral of W of t, and we're just going to accumulate that rate over the period from 0 to 10, and that'll tell us the total amount of words, number of words that the teacher has read in that 10-minute period. So we'll take the depth integral from 0 to 10 of the rate. And again, this is non-calculator, so we actually have to work this out by hand. But the good news is that it's just power rule. We do power rule 3 times, plug in upper and lower bound, and then there's no trig involved, so there's no need to go any further and deal with any trig, circle values. We can just leave our fractional values unsimplified, one big mess, and that would be fine. Okay, let's find the antiderivative first. So power rule, remember power rule, you're increasing your degree by 1. 8t becomes 8t squared over 2. 100 is a constant. It rises to be 100t. And then you're ready for your bounds. Upper bound first. I'm going to clean up, but you don't have to clean up. Just makes a little bit less things to write out. So 3's cancel out. Just plug 10 in. So negative 10 cubed over 10. We can leave that 8 over 2, or you can reduce it to be 4. Okay, so that's the result of my upper bound, and then minus parentheses on lower bound. The nice thing is, in this case, if I plug in 0, 0, 0, it's all going to zero out. And I'm going to leave my answer one big mess. I don't want to go any further if they're going to give me full credit here. And we just attach the unit that they want. This is the number of words, whatever this ends up being. If you want to know, it ends up being 1,300 words. But we want to take advantage of the fact that they will give us credit here, so why go any further? And we can just stop here and save time and move on if they're going to give us full credit at this stage. All right, next up. Number 4, continuous function f is defined on the closed interval from -6 to 12. The graph of f consists of 2 semicircles and a line segment shown. Let g be the function defined by g of x equals the integral from 6 to x of f of t. Find g prime of 8, give a reason for your answer. So remember, g prime means I got to get to the derivative first, and then I can worry about the 8. So my g of x, I'm going to write out g of x again just to reference purposes. So if I want to find g prime, I know I have to involve a derivative on this integral here. And we know a derivative on the integral will just wipe all this out. I'm just left with f, and then the upper bound gets plugged in, so f of x. So if I know g prime is f of x, now I have a way of linking between my g and f functions. So that means g prime of 8 is simply f of 8, and f of 8 is simply the y value of my f graph. So f of 8 is just 1. Find all the values in the open interval from 96 to 12 at which the graph of g has a point of inflection. Remember, this f is basically g prime. So remind ourselves that we're looking at the g prime graph. If we're looking at the g prime graph, then the way we find points of inflections, we find it by the max and mins, right? Wherever my g prime graph is experiencing a max or min is where my points of inflection is. So point of inflection of my g graph will be at -3, at 3, and at 6. So point of inflection exists at -3, 3, and 6. These are points of inflection since g prime changes between increasing and decreasing, basically the relative extrema of the g prime graph. Part C, find g of 12 and g of 0. Well, we have a formula to find any function off g function, so we just follow that formula. So upper bound is x, not 12 yet. Okay, so now if I want to find g of 12, I can just put 12 into my definition here. So let's see what the graph tells us. Between 6 and 12, that's just going to be this shaded region, and that shaded region is just going to be a triangle. I know area of a triangle is 1/2 base times height, so my my width is 6, my height is 3, so 1/2 6 times 3 is 9. So I have my g of 12. Next up, I want to find my g of 0. So again, follow the same definition. G of 0 is just from 6 to 0. Make sure that you always follow where the definition tells you. And if something is out of order, you can deal with that later. But don't try to do too many things at once. Just follow whatever the definition says. Okay, because I want to read the graph, I prefer to read the graph from left to right and not from right to left. And so I'm going to change the order of the bounds so that I don't have to worry about, oh, this is negative, that's positive. So I'm going to adjust the bounds. So now I'll just read my graph as I see it from 0 to 6. That's just going to be a semicircle, 1/2 pi r squared. My radius is just going to be 3. So 1/2 pi 3 squared. Don't forget about the negative that I'm keeping track of. So then I can leave it like that, or you can make it negative 9 over 2 pi. Either is fine. Part D. Part D says, find the value at which G attains absolute minimum. So another key word there. So there's another extreme value theorem. So notice how many times extreme value theorem can potentially show up on your AP exams. In this case, this is the second time we've seen it. So EVT, which means we need to test endpoints. Test critical points. But we're trying to find endpoints, critical points from a derivative graph. So let's create our f prime, or in this case, our g prime sign line, and therefore we can just grab our critical points from our g prime sign line. So let me label accordingly here. If this is my g prime graph, I want to remind myself above is positive slope, below is negative slope. Anything on the x-axis is slope 0. So I'm going from -6 all the way to 12. One critical point that I see is at 0. That's an x-intercept. Another critical point that I see is at 6. And let me draw my arrows here. So initially, I'm starting below the x-axis, so that's negative slope. Between 0 and 6, above the x-axis, positive slope. To the right of 6, still above. So the arrows are helpful because it kind of gives us an idea how our graph is moving, our graph is falling. Flat relative min rises and then continues to rise. So if I'm trying to find absolute minimum, I only have to worry about this critical point not about 6. If you tested 6, it's not an issue. You're just doing additional work, but we know that 6 is not going to be a relative min or absolute min because the graph is going to rise, flatten out, keeps rising. So I only have to worry about -6, 0, and 12. Okay. Test endpoints and test your valid critical point. And we have a formula for this that all go back into your definition here. So let's find g of -6 first. Okay, just following what the definition says here from 6 to -6. And again, I want to read the graph from left to right and not from right to left. So I'm going to change the bounds and pull a negative in front. So from -6 to 6, that's just going to be a semicircle below, a semicircle above. Notice these are basically identical. So this will just zero out, right? A negative area plus a positive area will just become 0. A -0 is still going to be 0. So I don't do any work there. I'm just call that 0. G of 0, we can just bring the data we found from part C, right? We have that data already. So -9 over 2 pi. That's nice. G of 12, we have that data as well. So we have some information we can reuse, which can save us a bit of time. So now we're comparing between these values and what's the lowest of these three. This should be easy to spot. We have a 0, a positive, and a negative number. The negative number is going to be the lowest, so our absolute max, sorry, absolute minimum. So the value is at -9 over 2 pi, but let's reread the problem here. It says find the value of x. So let's be specific here. Absolute min value at x equals 0. What they're really after is they're after the x value. So make sure you read the problem. Sometimes if they're asked for minimum value, then they're asking about the y value. If they want the x value, they have to specify. Okay, number 5. Okay, this is a particle motion problem here. Two particles, H and J, are moving along the x-axis. So keep in mind what H and J are doing. They're just moving horizontally. That's the only thing that I can do. Between 0 and 5, the position of the particle H is given by x of t. So I know the subscript looks intimidating or looks like it's confusing, but all it's doing is just trying to identify the different position functions for you. This is the x of t for position function for H, and they just want to highlight that so you don't get these two confused. So this is my position function for H, particle H, and then the velocity of the other particle is v sub j of t. So they're giving us information about both particles, but they're giving us staggered information. So they're giving us position function of one, but velocity of the other. Okay, so just keep that in mind. They're not giving us position of both of them. Just so they're purposely giving that staggered functions here so that we're able to seeing if we can keep track of the different relationships. Okay, so part A. Find the velocity of particle H at time t equals 1. So we're going to be finding v of t for particle H. And this is non-calculator, so we have to find the derivative first, and then we can plug in the 1. So x of t All right, so there's my starting function, position function for h of t, for particle h, sorry, particle h. And now I want to find v of t, right? So v of t is just the derivative down. So remember, the rule for e to the u is e to the u times u prime. So once we have our velocity function, we can find the velocity at that t, at that 1, and we just plug 1 in. You can leave your answer like this. This is non-calculated. I'll go a little further, but I don't think you have to. Okay, so any of these, I think, is fine. Remember, unsimplified is just as good as simplified. Unless it's trig. Okay, if you see trig, you gotta go one step further. So, for example, if you see sine of pi over 4, you got to keep going. You have to write it out as root 2 over 2 before you stop. Okay, so you do need to expand your trig. Okay, I know that's not related. I just want to just bring that up. Part B, during what open interval are particles H and J moving in opposite directions. So what we want to do is we want to take the velocity function for both, find the critical points, get our velocity sign lines to show up for both particle, and then we're going to line them up and see if we can see when they're both moving moving in opposite directions. Okay, so let me work on particle H first. Okay, so if I want to find a velocity sign line, okay, so my initial goal is I want to create velocity sign lines for both so I can line them up and actually see what's happening in terms of, when they're moving left and when they're moving right. Okay, so let me set v of t equal to 0 and see if I can find critical points. So the nice thing is I'm setting both equal to 0 here, but e to the anything is never equal to 0. No critical points are gonna come out of it. So e to the t squared minus 4t is never equal to 0, because if I try to bring that t squared minus 4t down by taking the natural log of both sides, natural log of 0 is undefined, so we're never gonna have to worry about this. So nothing will come out of it. The only thing we have to worry about is this other factor of 2t minus 4. Set that equal to 0. See what t we get. We get t equals 2t equals 4. And so therefore t equals 2. We have endpoints from 0 to 5. So let's create our velocity sign line for my particle h. So let me plug in 1. Remember, e raised to anything is always positive, so I don't have to worry about this. This is always positive. So if I plug 1 in, 2 times 1 is 1. 1 minus 4 is negative, so I know I'm moving left. If I plug 3 in to test positive here, 2 times 3 is 6. 6 minus 4 is 2. That's positive. So this is my sign line. I know that this particle H is moving left for the first 2 seconds and then stopping, turning around, and moves right for the next 3 seconds. Now I don't care about these test points anymore. These test points is just to help me fill out the signs, but my interval is from 0 to 2 moving left, and then from 2 to 5 is moving right. Okay, we'll keep that there, so we can reference it when we are ready to compare with what's happening with particle J. All right, let's build out our sign line for particle J. So we're going to take our velocity for a velocity for particle J and set that equal to 0. Set that equal to 0. Right, it's already in factored form, so 2t equal to 0, and then also t squared minus 1 cubed equal to 0. So here, that's just going to be 0. Here, if I take the cube root of both sides, I can get rid of that cube. Solve for t. Take the square root. I get plus or minus 1. But we have our bounds from 0 to 5, so we know -1 is going to be out, so just t equals 1. So we only have to worry about 0 and 1, but 0 is a duplicate because 0 is an endpoint. So really it's just 1. All right, so let's test 1/2. So if I plug 1/2 into my velocity function for particle j, 1/2 times 2 is positive. 1/2 minus 1 is negative. Sorry, 1/2 squared minus 1 is negative. 1/4 minus 1, that's negative. Negative cubed is still negative. Negative times positive is negative, so it's moving left from 0 to 1. Here, if I plug 2 in, 2 in for t is positive. 2 in for t here. 2 squared minus 1 is positive. 1 cubed is, sorry, 4 minus 1 is 3. 3 cubed is still positive. 2 positive is positive. So he's moving right from 1 to 5. Okay, so let me line up the two particles here. So this is particle H, and let me put particle J below, just so I can have an easier time comparing them. So when are they moving in opposite directions? Well, they're both moving left from 0 to 1 second, but then from 2 to 5 seconds, they're both moving to the right. But the only time when they're moving opposite directions is between 1 and 2, right? Because from 1 to 2, particle H is still moving left, but then from 1 on, particle J is already moving to the right. So we can say particle move in opposite directions between 1 and 2. Okay, so particle moves in opposite directions um, between times of 1 to 2. Since in this interval, the two particles have opposite signs for velocity. Part C. It can be shown that, I know it's hard to see, but that is meant to be a prime. It says V prime of 2 for particle J is greater than 0. Is the speed of the particle increasing or decreasing at t equals 2? So we're talking about particle J here. So here's V of t for particle J. Now we know that, let's figure out what V of 2 is. So V of 2 would be 2 times 2 times 2 squared minus 1 cubed. 4 times 4 minus 1 cubed. This is definitely positive, right? All we care about is that it's positive for now. Now they're telling us that V prime is greater than 2, is greater than 0, which really means acceleration, right? They're telling us that our acceleration is greater than 0. So now this is what they want us to want to ask us. Is the speed of the particle increasing or decreasing? Remember, if we're dealing with whether speed is increasing or decreasing, we compare signs, right? And because velocity is positive and acceleration is positive, they're both sharing the same signs. Therefore, we know particle J's speed is increasing at t equals 2. So speed of the particle J is increasing at t equals 2 since v prime of 2, or you can say acceleration at 2, and v of 2 have the same signs at t equals 2. Part D, particle J is at position x equals 7 at time t equals 0. Find the position of the particle. Show the work that leads to your answer. So we're looking for a position. We're given a starting position. We have velocity. This should remind us of applying that final equals initial plus displacement formula that we've seen in the past. So we're looking for x sub 2. We have x sub 0, and we just have to find that gap between 0 and 2 of my velocity function. And this is all for particle J here. So we're looking for x sub 2. We know x sub 0 is 7. We know that at time t equals 0, the particle is over here at 7 on the x-axis. And we just have to figure out the depth integral or displacement from 0 to 2 of my velocity function under my J particle. And this is non-calculator, so this is where we have to work this out by hand. And typically, as I said before, that you're most likely going to see at least one U substitution problem that you got to go through in your non-calculator section. And this is going to be a U substitution problem. Okay, we have to make sure we remember the bounds are not going to be involved until we get to the antiderivative. So we'll pick out our U value. Our U value is what's inside the parentheses. We're going to cancel out the T's, take the antiderivative power rule, then plug in upper bound minus lower bound. Okay. So all of our work is really just trying to get this to give us a number. Okay. I'll bring this over here, show my work here. Okay, replace the parentheses with U. Replace dt with du over 2t. Get the t's to cancel out, but there's a bonus here. The 2's also cancel out. So in this case, no leftover coefficient to keep track of. Just have to take the integral of that u cubed. Okay, everything is cleaned up, ready for our integral rule. U cubed becomes u to the 4th over 4. We have our antiderivative. We're ready to work in the bounds, but there's a mismatch of variables. Let's bring back the variable that we want. So let's bring back variable in terms of t. Now that we have the variable that we want, we can work the bounds in. So 0 to 2. Upper bound first. Careful, the 0 is not going to wipe everything out. So 0 is going to have something left over here. So 0 minus 1 is still -1. So 4 minus 1 is 3. 3 to the 4th is 81. And 80 over 4 reduces to be 20. So the result of my displacement is 20. I have my initial location of 7. So let me recap here. So x of 2 is therefore x of 0, which is 7 plus, and all this work gets us to a displacement of 20. So that means this particle starts off at position 7, and then over the next 2 seconds, he's going to move to the right 20 units. And so at 2 seconds, he's going to be at location 27. Okay, find the position of the particle of j at time t equals 2, and then we've shown the work that leads to our answer. All right, number 6, page 28. All right, still non-calculator. Last problem for AB. Consider the curve G defined by the equation y cubed minus y squared minus y plus 1/4 x squared equals 0. Show that the derivative is equal to this. So we're going to find the derivative, and they're telling us what the answer is going to look like. So we have to explore, okay, what derivative are we going to have to involve to get to this form? And one thing that we recognize is, okay, definitely power rule because we have all these individual terms, but we also see a bunch of y variables. So this is going to have to involve implicit. Right. So we're not going to work with this. Okay. I see students in the past, they would try to take the antiderivative. And so you're not going to touch this at all. You're just going to be starting here and work to find the derivative and try to get the derivative to match this answer. Okay. So you're not going to start here. You're going to start with this function. Okay, so derivative, we see 3 y variables, so that means you're expecting 3 dy dx to show up in your derivative process here. All right, so y cubed becomes 3y squared, which is going through power rule, but we're asking for y's derivative here, so make sure you attach a dy dx. Y squared's derivative is 2y, also involving y, so we need to include dy dx. Y's derivative is 1 times dy dx. I like to put a 1 here because eventually when I factor the dy dx out, I don't want to lose the fact that there's a placeholder. So anytime a y is by itself implicit, I like to put a 1 dy dx so I don't lose track of that, that value. Okay, we're done with the y's. Our 3 dy dx's have shown up. We still have to do power rule for 1/4 x squared. Okay, so now we're done with the calculus. We're just algebraically trying to isolate the dy dx. So I'm going to move that 1/2 x or 2/4 x over to the right. And then I'm going to factor out dy dx for the rest of these terms here. So we're almost there. Just have to divide by the whole parentheses to get that dy dx by itself. So just divide that over. So we're basically there. What they're doing here is they're just pulling that -1/2 out in front and letting that 1/2 multiply by this. But I think this is essentially the same thing. Um, uh, I'm going to say that they will give you credit here, but just to be safe, you could do this as well. You can just think of that -1/2 as getting pushed out in front. That's basically your dy dx there. And you can write it exactly like that. But I'm pretty sure they will give you credit if it's in this form as well. But if you want to be safe, then maybe just go all the way to here. Part B, there's a point on the curve between near -2 or 2 -1 with x coordinate 1, 6. Use the line tangent to the curve 2, -1 to approximate the y coordinate of point P. So this is simply a linear approximation. We're going to take the order pair 2, -1, put it into the derivative to get our slope, and then do point slope form. And then once we get point slope form, um, then we can plug in 1.6 at the end. So let me just show the steps for my key. So here's my order pair, 2, -1. Here's my derivative function, -x/2 times 3y squared minus 2y minus 1. I'm just going to take that order pair and put it into my derivative to get my slope. So -2/2 times 3 times -1 squared minus 2 times -1 minus 1. I prefer to clean this up just because technically you don't have to, but I think it's going to be a little bit cleaner, just to be able to present our answer. So rather than have to write all this out. So I think it's going to be, for this part, I think it's beneficial to just get it down to a number. So -2/8 is -1/4. So we have our slope, we have our order pair, get it into point slope form. Y minus y sub 1 equals m times x minus x sub 1. Let me just get that y by itself. And then my final step is my linear approximation. So I'm going to just insert that 1.6 into my x. And now I can just leave my answer unsimplified. So I will leave my answer in this form. All I'm doing is replacing that 1.6 in for x. Part C. For x greater than 0 and y greater than 0, there's a point S on curve G at which the line tangent to the curve is vertical. Find the y coordinate of point S. So anytime you're dealing with a derivative and you're asked about vertical or horizontal tangent, here's something to keep in mind. If I want to find a horizontal tangent, you want to set the numerator of your derivative equal to 0. Okay. But if you want to find the vertical tangent where your slope is undefined, you're going to be focusing on the denominator. You want to set the denominator of your derivative equal to 0. Okay. In this problem, they're only asking about vertical tangent. So we're going to be focusing on this strategy here. Okay, vertical tangent. So we're going to take our attention to the denominator of the derivative, set that equal to 0, and solve for y. If I divide by 2, or let me just, I can just factor this, right? Three y squared plus 1y minus 3y minus 1. So this is a factored form. Solve for y. It says for x greater than 0 and x and y greater than 0. So we can't, the negative 1/3 is not going to fit that criteria. So the only y coordinate of vertical tangent is at y equals 1. All right, last one. Particle moves along the curve h defined by the equation 2x plus natural log of y equals 8. At the instant when the particle at 0.41 dx dt equals 3, find dy over dt. So this is going to be related rates, okay? And we got through this entire FRQ without even seeing one related rates, but you know they're going to have to slip it in somewhere. So it's very unlikely that you're going to see the entire FRQ without at least one related rates, and this is where um, uh, related rates is going to occur. Notice that they don't tell you it's related rates, but they give you enough context clues. They give you dx dt or dy dt. Other times they'll give you with respect to time, or they'll say they'll give you a bunch of information with time involved, like inches per second or meters per second. So expect at least one related rates to show up on your FRQ, even if it's not an extended problem devoted to related rates, but you're more than likely going to have at least one related rates within your FRQ experience. Okay, so part D. So related rates means we're going to find the derivative, but time is going to be our independent variables. So we want our dx dt and dy dt to show up as we build our derivative. This is not implicit, meaning that we're not just involving y and turning that into dy over dx. Every variable is getting impacted. So you're going to expecting a dx dt, a dy dt, and a dy dt as well. But besides related rates, the other complexity is understanding, okay, there's also a product rule that we have to understand that's involved because two variables are getting multiplied. Okay, so f prime g plus fg prime. Okay, 2x becomes 2. Remember related rates here, so dx dt. G function f function, and g prime, y becomes dy dt because time is impacting, is the independent variable here, not x. Natural log of y, derivative of natural log is u prime over u, so 1 over u or 1 over y, dy dt, and then this 8 goes to 0. Okay, so they tell us dx dt equals 3. We know x is 4. We know y is 1. And then we just find dy dt. So everywhere we see dx dt, replace with 3. X and y replace with 4 and 1. And then we should be left with just dy dt that we can isolate and solve for. Unreduced is fine, so negative 6 over 9 is fine. All right. Good luck, AB students. If you have any last minute questions, I'm available tomorrow morning, 7 to 7:30. But otherwise, hopefully, you can get a little bit more studying in and get a good night's rest. And good luck to you all tomorrow. So I'm going to shift over to the BC problems from 2025. All right, so this is page 33 in your packet 7, number 7. Curve C is defined by the polar equation R of theta. Circle C and the semicircle R equals 1/2 between 0 and pi are shown. And again, they're nice to remind us to be in radian mode. Find the rate of change of R with respect to theta. Show the setup for your calculations. So I like to stay in rectangular form. I just don't feel like I have to spend all this time trying to get into polar form when I don't have to deal with this in terms of theta. I can just do this in terms of x. So I just had it as 2 sine squared x. Math 8. One 1.031. Find the area of the region that lies inside curve C, but outside the graph of polar region R equals 1/2. Show the setup. So we basically want to do this, right? We want to remember with polar area, we're accumulating these sector regions, these pizza wedges from, but we first have to accumulate more than what we need, right? And then we can subtract out the parts that we don't want. Remember, any polar area that you find, you have to involve polar zero. So we have to create two integrals here. One that will find more than we need, and then another integral. But first, we need to find intersections, right? We need to figure out, where do we begin and where do we end, right? We need to find our theta sub 1 and our theta sub 2. So we're going to have to set these two equations equal to each other. And solve for x. So again, I like to do it in the rectangular form. I'm just going to solve for x here. So I'm graphing this and looking for my x-intercept. I need to go from 0 to pi. Oops. Point 523, that's one of them. The other one, I'll hit enter here. And to the right, hit enter again. 2.6. Okay, so I know my area region will be between theta sub 1 and theta sub 2. So my full area will just be more than what I need from 0.523 to 2.167 or 2.16179. My big region here is that 2 sine squared, r squared. So even though I'm doing this in rectangular form, I do want to give the notation, the variables that they're referencing. So I'm putting it in terms of theta, but in my calculator, I'm doing it in terms of rectangular form, in terms of x. So this will give me my entirety region, but I just want the region without that portion, with this portion removed. So I'll subtract that out. Or 2.6, my bad. Copy this, 2.6. And this will give me an area of 2.066. Part C, it can be shown that dx over d theta, okay, given, between 0 and pi over 2, find the value of theta that corresponds to the point that is farthest from the y-axis. That farthest should remind us of extreme value theorem. We're going to be involving extreme value theorem. So we're going to figure out where that is equal to 0, find critical points, and then we can put it into our x equation. So let's understand there's EBT involved. Set dx over d theta equal to 0, and look for critical points or x-intercepts. I think the only way to do a cosine squared x is to do a cosine x in a big parentheses squared minus 2 big parentheses sine of x, close that off, and then cube it. And I want to look at this between 0 and pi over 2. Well, let's do from 0 to pi. It doesn't matter here. Actually, I do want to adjust my x max to be pi over 2, so I'm not having to look at anything more than for past that endpoint. Okay, so that's the only point I need to worry about. So second trace 0. .955. That's the only critical point, but we also need to involve 0 and pi over 2. Or sorry, theta. Even though I'm doing this in terms of x, I do want to match the variable with what they're talking about. So find the rate at which origin with furthest from the y-axis. So furthest from the y-axis, we want to find the largest x value. So to get the largest x value, we need to create an x equation. And we know that means we have to get from polar into rectangular form. And polar into rectangular form is x equals r cosine theta. And we're talking about curve C here. And curve C is built off of the sine one. So the r we want to choose is the 2 sine squared theta. So this is the equation that we want to test with our endpoints and vertical points. We want to find the x value that's furthest away. So the largest x value given these theta. Okay, so we'll test x of 0. We'll test x at 0.955. And we'll test x at pi over 2. Now for trace y1 of 0, I get 0, 1955, 0.769. And then at pi over 2, I get 0. So max occurs at, find the value of theta. So max occurs at theta equals 0.9553. Max, let's see, distance. Part D, particle travels along the curve so that d theta over dt equals 15 for all times t. Find the rate at which the particle's distance from the origin changes with respect to time. So that's a big hint that this is going to be involving related rates here. Okay, so we have to build out our derivative using related rates. So here is my r of theta. I want to find the derivative, but then I want time to be the independent variable. Okay, I'm just getting ready for what I'm expecting to see. I'm expecting to involve chain rule. So r becomes dr dt, right? Related rates. And chain rule. So outside derivative, well, outside portion is that 2 brackets squared. Inside portion is that sine theta. To make sure I take turns with these derivatives. So 2 parentheses squared becomes 4 parentheses to the first power. And then sine's derivative is cosine. But remember, time is involved here, so theta becomes d theta dt. We know d theta dt equals 15. We know theta is 1.3. So now we're just plugging everything in to solve for dr dt. All right. So number 5, this is page 34. This is now moving into non-calculator. So 5 and 6 will be non-calculator. Let y equal f of x. be the particular solution for dy dx with the initial condition. Find f double prime of 1. We already have y prime, so to get to y double prime, we have to find the derivative again. And another implicit will be involved because there's y, and then also we see there's a need for a product rule as well. Hey, f prime, 3 minus x, that just becomes -1. G stays, f stays, and g prime, y squared becomes 2y. We're asking for y's derivative with respect to x. This is where dy dx. So now we want to find the second derivative at 1, -1. So I'm just plugging in all the x's and y's with 1 and -1. Now dy dx is this 3 minus x y squared. So I'm just going to step to the side here. Dy dx at 1, -1 is 3 minus 1 times -1 squared, which is just really 2 times 1, which is 2. So I'm just putting that dy dx here as times 2. So -1 times -1 squared, that's just -1. 2 times -2 times 2. -1 minus 8 is -9. I think technically you can leave your answer unsimplified. I just feel like if it's not too much trouble, I like to get it down to a number, but I think this is fine. Yeah, it just feels a little bit cleaner. Now, if this is too much trouble, then I definitely don't want to simplify it, fearing that I might make a mistake. But it's really up to you. If you feel like it's just cleaner, that you want to clean it up, you can. But if you feel like I don't want to mess with something that's already correct, fine. But I just decided to go a little further, but this is fine. Part B, write the second degree Taylor polynomial for f about x equals 1. So think about your Taylor polynomial formula. So that means my second degree Taylor polynomial will just be my f of 1 plus f prime of 1. This is centered at 1, so times x minus 1. And then f double prime of 1 over 2 factorial x minus 1 squared. Right, so really we're just trying to find a suitable replacement for these parts. And these really are the only things that we have to find a replacement for. Oh, I see now. Yeah, so it's really beneficial to get this down to a number because then that makes plugging that in a little cleaner rather than trying to plug all this into that space. Um, so I think for us, it is going to be a little bit cleaner. There's less things to write out to have that cleaned up so we have it ready for part B. So f of 1, they tell us is -1. F prime of 1, which is a dy dx at 1, -1. We found that as well, which is 2. And then we just found f double prime of 1, which is -9. Right? So f of 1, f prime of 1, f double prime of 1, part C. The second degree Taylor polynomial for f about x equals 1 is used to approximate f of 1.1. Given that the third derivative is less than or equal to 60, use Lagrange error bound to show that the approximation of f of 1.1 differs by at most 0.01. So we know that our remainder or second degree Taylor polynomial is going to be off by no more than the maximum of the n plus first derivative, which will be the third derivative, evaluate z over 3 factorial x minus c to the third. So let's find our c value and our x value to plug in. So we know that we're centered at 1. That's our c value. We know our x value is 1.1. And then we know the max is going to be 60. So let's just plug everything in that we see here. So 60 over 3 factorial, x minus c, so 1.1 minus 1 to the third power. That's going to be 60 over 6, 3 times 2 is 6, over 0.1 to the third. That is less than or equal to 0.01. And it ends up being 10 times 0.1 to the third, which is 0.01. So you can work that out or just trust that is going to be the same or less than or equal to. Part D is Euler's method. So two-step size. So my A value is 1, my B value is 1.4, my N value is 2. Just working through my chart here. The thing to be careful about with this problem is that this is non-calculator, so we do want to take advantage of leaving our answer unsimplified. And I remember students talking about this last year where they were spending all this time trying to clean up, and then they forgot that they could leave their answer unsimplified, so they're trying to add up all these decimals when they've already arrived at the answer. So just be aware Sometimes we hope that Euler's method shows up on the calculator, but if it doesn't show up on the calculator section, then try your best and know that it's a little annoying without the calculator, but you can take advantage of the fact that you can leave your answer unsimplified, so that can hopefully save a little bit of time. Okay, so our x value is 1, our y value is -1. That's the starting point. We know our delta x, b minus a over n, 1.4 minus 1 over 2. 0.4 over 2 is 0.2. So 1 to 1.2, 1.2 to 4. And then now we're working our way through our chart here, our table here. Our dy dx at 1, -1 is 2 because we found that over here. So now y equals y sub 0 plus dy dx, delta x, so -1 plus slope times step size, 0.2. This one I think is beneficial to actually work it out. 2 times 0.2 is 0.4. 0.4 minus 1 is -0.6. So now we put that -0.6 here. So now this becomes a little messy here. Putting that 1.2 and -0.6 into the dy dx, we'll get 3 minus 1.2 times -0.6 squared. I don't want to spend the time trying to multiply all this dy dx out. So I'm going to take all this and put it into my formula here. So my y sub 0 is -0.6 plus my slope times 0.2. Thankfully, this is as far as I need to go because this is basically my y value at 1.4. So I'm going to leave my answer unsimplified. This is my y value. Okay, number 9, which is number 6. All right, Taylor series for the function f about x equals 4 is given by, okay, convergence f of x on the interval, its interval convergence. Using the ratio test, find the interval convergence Taylor series for f about x equals 4. So we're going to go through ratio test. Okay, my a sub n plus 1. Replace every n with n plus 1. N plus 2 times 3 to the n plus 2. Sorry, 3 to the n plus 1. Times or divided by my a sub n, which is the same thing as multiplying by the reciprocal of my a sub n. I'm sorry. Okay. All right, let's see what all cancels out here. X minus 4 to the n can go away. 3 to the n goes away. X minus 4, at least one pair goes away. And then I'm left with n plus 1 over n plus 2. And because these are both increasing at the same rate, they're both, as n approaches infinity, the ratio of my coefficients is just going to be 1 over 1. So I know this will just become 1, so that goes away as well. So the only thing that's left is x minus 4 over 3. And our condition is less than 1. So let me move that 3 over. That is in the form of x minus c is less than r. So this is going to be your most familiar interval convergence, where it's going to be clearly between two uh, real values. So I know my ratio is my radius is 3, and then my center is at 4. Let's build our potential interval of convergence. Add 4 to every side here. So our interval of convergence is at least between 1 and 7. We just have to worry about, do we keep the 1 and 7 as well? So back to our original rule of sequence. Let's test x equals 1. One minus 4 is negative 3. Now this is the same thing as negative 3 to the first power times negative 3 to the n. And then negative 3 to the n and 3 to the n, they both are sharing the same exponents. So I can think of it as negative 3 to the first power times negative 3 over 3 all raised to the n, right? Because these are both sharing the same exponent. So this really just becomes negative 1 to the n. And I still have the n plus 1 that's sitting there. So if we play with this a little bit here, this is still an alternator because this will give me negative 1, then becomes positive 1, then negative 1, then positive 1. So this keeps changing signs, and a negative times negative is positive, and a positive times negative is negative. So ultimately, this will still do the work of getting an alternator to show up, or alternating signs for every subsequent term. So this is alternator, and then all I need is that 1 over n plus 1 to approach 0, and it does. So this converges by AST. So we're going to keep x equals 1. Okay. Next up, let's see what 7 gives us. So 7 into my rule of sequence. All I'm left with is 3 over n plus 1. There is no alternator. This is basically in the family of 1 over n, and we know 1 over n diverges by p series. We could convince ourselves by going through limit comparison test, compare this with 1 over n, but If you recognize, okay, this is basically P series, my p-value is equal to 1, I can say converges here and diverges here. Okay, part B. Find the first three non-zero terms and general term of the Taylor series for f prime. About x equals 4. So we just have to take each of these terms here and find the derivative, and also find the derivative of my general term. So just do power roll, bring the 2 down. Two comes down, 2 becomes 1, bring down the 3. All the coefficients in the denominator just stays. That's the same thing as times 1 times 1 over 3 times 3 squared. So the denominator is not going to change. Okay, also apply power rule for the general term. Bring down the n plus 1, subtract 1 from the original exponent. Uh, we don't have to reduce, but I do want to show you the benefit of reducing, maybe not the first three terms, but at least the general term. So but I just want to show you that no, this is fine. This is but let me show you what the benefit of reducing that general term is, especially for the next problem. So if I were to reduce this, that ends up giving me x minus 4 to the n over 3 to the n. Okay, just wanted to have that available for the next problem here. So now part C, um, the Taylor series for f prime described in part B as a geometric series. For all x in the interval, show that f prime is equal to x minus 4 for x minus 7 minus x. So they're connecting this with geometric series. And if you look at the general term here, the cleanup version kind of reminds you of a geometric series, because we can think of this as x minus 4 over 3 raised to the nth, right? So this is my common ratio raised to the nth. This is now my my common ratio. So if part C wants us to basically build that a sub 1 over 1 minus r and show that my my sum can equal that, then let's gather our information, right? So keep in mind, we're kind of working with this idea of geometric series. We know that a sum of a series is a sub 1 over 1 minus r. So my a sub 1 for my f prime is whatever this is, right? And I want to hold on to my x. I don't know what my x is, but I know I can reduce the 2 here. So my a sub 1, my first term is just going to be x minus 4 over 3. My common ratio is also x minus 4 over 3. So I'm just have to put it into this infinite series sum. A sub 1 all over 1 minus r. My r is So now the hope is that after we clean this up, it'll match what they want us to match with. So let's see if we can get there. So one thing I see is I want to try to, before I multiply and divide by the denominator here, I would like to get this down to one fraction so that it's cleaner when I multiply by the reciprocal. So let me work on my common denominator here. So this is the same thing as 3 over 3 minus x minus 4 over 3. So if I were to clean that up, 3 minus x plus 4 becomes 1 minus x over 3. Oops, sorry, my bad. 3 plus 4, 7. 7 minus x. In the numerator, we're still going to keep it as x minus 4 over 3. So now I have a little bit cleaner complex fraction here, just a fraction over a fraction. So I'm going to take this and divide it by this, which is the same thing as this, multiplied by the reciprocal of that. Threes cancel out. And we're able to show that my f prime is this. All right, simply by gathering the data like we would from a geometric series. A sub 1, common ratio, a sub 1 of 1 minus r, clean up, and match their problem. Or match their version of the sum. It is known that the radius of the convergence of Taylor series for f about x equals 4 is the same as the radius convergence of the Taylor series for f prime about x equals 4. Does the Taylor series for f described in part B converge to f prime at x equals 8? Give a reason for your answer. This one is quick because since the interval convergence is between 1 and 7, f prime will diverge outside of that interval. So since we've already established that interval convergence from 1 to 7, f prime is also going to have to live within those rules as well. Okay, I was thinking that maybe I had time to do the 2024 BC FRQs, but I think I'm going to stop here. If you look on the BC page under May 10th, I have links to the 2024 FRQs. So if you're wanting to work through those or check the key is available, but I have the video available from what I recorded last year. So I will put this video up. I'll save it and I'll upload it under that May 10th date. But yeah, if you have any last minute questions, I can be available tomorrow morning between 7 and 7:30. Otherwise, hope you guys get a good night's rest and good luck tomorrow. Hope you all do well. All right, good night.